So today I'll be talking about from synthetic data to mixed reality. But frankly, it's all going to be about synthetic data. There won't be much mixed reality. I work at Meta. I'm an engineering manager. My team does research on different aspects of synthetic data, domain adaptation, bridging this gap between synthetic and real. And I'll be mostly talking about that in the next few slides. Slides are not changing. All right. Okay, let's talk about the problem. In general, most machine learning researchers, scientists, engineers, or practitioners, they always have this data problem. I mean, it's no surprise that Andrew Ng has been pushing for data-centric focus on AI. But there's a problem with real data. First of all, it's expensive to acquire, to get, and it can take large amount of cycles. And even if you acquire these data, they're very costly and error prone. And, this gets into this endless feedback loop of, going over to your contractors, to your, vendors and trying to fix data, and that can take months, years, God knows how long. And then beyond that, even then you have diversity issue. For example, you cannot just collect all possible data. So you'll always have gaps, you'll always have diversity issues with your data. And these rare scenarios are even harder to acquire in reality. And then beyond all those things, you have privacy issues that comes with real data. And something a problem we have in mixed reality or VR, AR space is that our sensors keep changing and they keep rapidly evolving. So whatever data you collected may not just work. All right. Let's talk about synthetic data. So synthetic data is a most promising and viable solution for this data problem. I mean, you can create this data by yourself, with the help of our artists or simulators. And you can create very high diversity of data. You can get varying perspectives. You can even collect data for, rare scenarios. Even for, maybe it's hard to acquire data for, deep sea diving or even Mars exploration and whatnot. You can get all this data very easily using, using these engines, game engines, and even these rare and black swan events. And there is fewer or relatively fewer privacy issues with synthetic data because, we are creating them. So these are the advantages of synthetic data. For the rest of the talk, I'll talk about, what are the problems with synthetic data. Okay, let's talk about the synthetic data pipeline real quickly. So we have different parameters, which parameters of generation, as we call it, which can be number of objects, their position, placement, when you're generating scenes. If you're creating simulations with digital humans, it could be different parameters, trajectories for humans, facial expressions and whatnot. And they go through rendering pipeline, and you get data out of it, which can be in the form of images and then different ground truth, different ground truth and different aspects of, the ground truth, like semantic segmentation mask, and all kinds of things that the machine learning engineer researcher cares about. Let's talk a little bit about learning from synthetic data. How do we typically learn from synthetic data? So there are two typical settings. One is the fully supervised settings where you have both real and synthetic data available to you. And then synthetic data is filling in the gaps of real data, so you can have mixed training for your models. I'm primarily talking about computer vision here. So different kinds of mixed model training. Maybe you can use large amount of synthetic data for pre-training and those aspects of it. And ultimately, you combine both synthetic and real data to achieve the highest KPIs or use cases or experiences, whatever you care about. The second setting is that there's no labeled real data, and in that case, there are different ways to leverage synthetic data to train your supervised models, and unlabeled real data can come into either come in as a pseudo labels using domain adaptation based on techniques, or can come in many different ways. But there's also that setting which people typically use. Okay. So we spoke about synthetic data, what are the advantages and, over real data and, how it can really affect each and every ML practitioner. But let's talk about issues with synthetic data. There's no free lunch, right? So um, in general, synthetic data suffers from something called domain gap, where when you train a neural network model on synthetic data and when you evaluate or deploy it in real world, you suffer from something called performance gap, reality gap, which we call as domain gap. Now, bear in mind that domain gap happens also with real data. Like if you train a model in Tokyo based on annotations and deployment in Tokyo, and you deploy it in San Francisco, you're still going to have model failures. You're still going to have gaps and issues, right? So domain gap happens with all kinds of data. However, with synthetic, we have the power to do something about it because the generation is easier, and we can actually change it in a way we would like. In general, we think of domain gap as two kinds of domain gap. One is appearance and content. That's what researchers argue. Content is, the distribution gap between, the position, pose, placement, geometry, different kinds of dynamics of scenes with synthetic and real. And appearance is simply how synthetic and real data differ in appearance, like color, texture, light conditions, sensor noise, and all kinds of things. Basically, appearance and content. Okay, so for next of the slides, I'll talk about, given these domain gaps, which happens between synthetic and real, how do we bridge them? So, a straightforward technique is something we call as domain randomization, which bridges this appearance and content gap both. And then, there are other techniques like domain adaptation, like image-to-image translation. You can also deploy generative models to create the data directly, synthetic data directly, learned from real world. And you can deploy some other domain adaptation techniques like pseudo-labels. Okay, let's first talk about how do we bridge the appearance gap. So in this example, there are many ways to do it in the literature. I'm just going to go over the most popular technique, which is image-to-image translation. In image-to-image translation, what happens is you have a GAN-based framework typically, and a generator takes in your synthetic images and translates them to appear like target. In this case, a target is a real image, and source is a GTA 5 image. And the translated image starts to look real, which is just like the target image, and in this case, it's Kitty. And a discriminator just distinguishes between the translated and target and says whether the image is real or fake, or whether it comes from source or target. So this is the most popular technique, and to bridge this appearance gap. So one of the papers actually we published last year in CCV was. When we do this image-to-image translation to make images look real, photorealistic, it causes some kind of artifacts and corruption, right? That happens because of the way the GANs work. So one of the challenging tasks we had to deal with was how to make sure that when we do this translation, we do not cause any corruption. Now, what is the problem with corruption? If you cause some corruption in the translation, your label, because you're going to use this data for training your computer vision model, and when there is a corruption, your labels are going to become invalid. And when your labels are going to become invalid, then your downstream task will suffer. An example of invalid label would be a tree appearing in the sky. The tree will be real, but it's out of place, and as a result, it affects the downstream performance. So we created this method to address this problem, and it works well. Okay, another popular technique for bridging this domain gap between synthetic and real is this student-teacher paradigm, which I was talking about previously. You have unlabeled real data, you have some synthetic data, you train a student-teacher model to extract pseudo-labels from real data, then you further filter those pseudo-labels to throw away bad confident ones and keep the ones which we are absolutely confident of. And then again train the student-teacher domain adaptation model with the pseudo labels plus synthetic data, and goes through several loops. Okay, I spoke about appearance gap, and I spoke about this domain gap and how do we bridge this appearance gap. But a bigger challenge that we have in synthetic data community is content creation, and how do we address this content gap. So the remainder of the talk will be focused on how do we bridge this content gap. So let's talk about what is the problem with this content gap. So when you look at synthetic images and real images, there is a big gap between the two. Synthetic rooms often look very clean. There is no mess. Does not have a large amount of diversity. Like if you look at real rooms, there's stuff throwing around, and especially if you're a young parent, this happens all the time. So if you're going to deploy your models on these kind of real data, good luck with that. Now, addressing this sort of gap is extremely important for synthetic data creators. Now you can go ahead and create a digital twin for it in synthetic, but it's going to be extremely expensive to do so. So that's not the most viable way to do it. Another problem is that the content creation I was talking about is very expensive from artists. So we have to hire a lot of graphics engineers, experts, artists to create this kind of content. And it's extremely expensive to create this content. I'm giving an example of GTA 5. GTA 5 took 3 years, millions of dollars, and thousands of developers to actually create this. If you were to create full simulations like this, it's better to just get real data. This really lessens the appeal for synthetic. So what do we do about it? Well, one of the most popular technique to address this is called domain randomization. So let me explain what domain randomization is. You create a scene graph for your scene or venue or anything that you're working with. Could be a dynamic graph as well for full simulation. And you randomize the parameters of the simulation or the scene within realistic bounds. So you create random light, random texture, random position, random pose, random objects, but make sure these are within the realistic bounds, as the car suddenly doesn't start flying in the sky, but as long as the car stays on the road, it respects the scene graph. You can randomize all positions of the car. And then add distractors. Now, this kind of techniques for content creation is much more cheap as opposed to building full simulation like GTA 5. You can get results and achieve even better results than GTA 5 in a matter of weeks to get this. And this is a very simple and effective technique. However, the synthetic data does not match the distribution of real data, and there is still a gap. So it works well, but there is still a gap. And other than that, how to determine this bounds automatically is another challenge, because you have to do experimentations, and they're also very expensive. Okay. Another great way to create content which is primarily used in graphics community is procedural generation. Artists use tools like Houdini to create large amount of diversity corresponding to a single style or a single object. In this case, we're showing some 3 examples, which has been randomized or created using Houdini-like tools, using procedural generation. So this is creating a generator is expensive, but once you have a generator for an object of interest, you can create a very large amount of diversity. So this is an effective technique for scaling your content creation and bridging the gap from real world. Procedural generation can also be used to add clutter and the mess into the real scenes. As we saw, real scenes are messy. You can use procedural generation to create large amount of clutter, large amount of diversity, and you could control it and so on. So this helps bridge some of these gaps. But the challenge with procedural generation is that procedural generation can also be used for generating human trajectories, with collision avoidance. You can move cameras, you can generate human trajectories, you can create dynamic scenes with procedural generation. So almost everything can be done procedurally. You just have to put these rules in your system. Now, I'll talk about the challenge with procedural generation. So great way to scale content, great way to reduce the domain gap. But it's it's manual rules-based system. So there is a human bias that we are adding to our data, because an artist will have their own imagination and they will think what it should look like, and there's a human bias and set of rules being encoded, and that's not really great for machine learning models, because machine will be biased towards whatever rules have been encoded by artists or graphics engineers. So what do we do? Well, we can let the networks design their own data. I mean, that's another approach. We think if humans are biased, maybe the networks will be better. So there has been some work in this regard. I've cited two work here where you can use network to learn to generate your synthetic data sets. So you can automatically learn the target distribution that in this case is primarily content. So you can learn the pose distribution, position distribution, number of objects, types of objects, size, scale, all kinds of problems. And typically it's done using the two works I've cited. Is like, one is where you can you do require some small amount of annotated real data set, which acts as a task class. And then you have some kind of distribution loss. And the other method is done using a self-supervised loop and does not require any real data set. So in either case, you create this end-to-end system where you learn the distribution of target data sets, but you deploy a game engine in the process, or a differentiable render-based engines. So they both work well, and it's able to learn to automatically generate scenes. However, there's still gaps with real data. Does it work as well as real data? The answer is no. So what do we do then? Another great work that came out, I think a year or two ago, was this work called ATISS, Autoregressive Models for Indoor Scene Synthesis. So there are many works out there that use machine learning models to do indoor scene synthesis. So compared to previous work, it does not require any game engines, any complex systems. It can just be learned. So you can learn all the distribution, your room composition, and everything directly from a network. And this particular work uses some kind of autoregressive, set generation-based transformer models to do so. But there are still problems with it, right? So great that it does not need game engines and all those, the complexity. But the rooms that are being learned are still relatively simple, and the content is, of course, simple, and at the same time, it does require some supervision. And again, if we're going to use supervision to create synthetic data, then kind of defeats the purpose of using synthetic data, because we don't have supervision. So another interesting work that we published, I think 2 years back, was using GANs to create synthetic data, but using unlabeled real data completely. So we use BlockGAN here, which is controllable 3D aware GANs that can be used to create large amount of synthetic data, and you can also get labels out of it. So not only you get, like, obviously GANs can create a large amount of images, but you can also get labels out of it, and then you can use that to train your downstream task. But the problem with this method is that it does not generate complex scenes, and it also is limited to fewer objects. So only in this particular case, it did 2 objects. Okay, another exciting work that I was the most excited about, which came around last year, was using GAN, dataset GAN, where you can have some annotation in the latent space. In this case, they use style GAN to create large amount of images and corresponding labels, and then use it for training downstream tasks. So they do require some amount of labels, but at the same time, they can create unlimited amount of synthetic data, in this case faces with part labels, and they trained it for downstream tasks, and they achieve pretty compelling KPIs. So this is another great amount of work. Okay, so I'm entering the final stages of my talk. So I spoke about domain gap, I spoke about synthetic data, and then I spoke about domain gap. How do we bridge the appearance gap? How do we scale content? How do we bridge this content gap? Now, I didn't really cover other set of things that happens in the VR space or mixed reality space, which is camera simulation. There is gaps, domain gaps there as well. There is environment simulation, there's animations, and so on. So I didn't get to cover, but there's all kinds of dimensions to synthetic data. And putting it all together, we have these generation parameters that we use. We do domain adaptation, we do bridge the domain gap, we do all those things, and we simulate all the devices or sensors, and then we run human animations. We make sure there's a lower domain gap on animations as well, and get it all together to yield some kind of synthetic data simulation. We get the simulation out, we get the ground truth out, we get all the labels out, we train our downstream task for mixed reality models, and then and that's pretty much the goal of our work. Okay, final remarks. Is that I covered synthetic data, advantages of synthetic data, lots of diversity, rare events, no privacy issues. We spoke about some of the issues with data generation pipeline. Then we spoke about how to bridge this domain gap between synthetic and real. We covered domain randomization, procedural generation. We spoke about distribution, machine learning based methods to create synthetic data automatically. And then we spoke briefly about domain adaptation, image-to-image translation, and at the end we try to put it together as a simulation we use for training, models, computer vision models for VR/AR tasks. Thank you.